Okay, welcome everyone again. So on our fifth lecture, this is our lecture 5, and as I have told earlier, today will be this will be a very important. What we will learn today? So basically we will learn how to solve differential equations. So this is the core concept in so if you want to work with this harmonic, if you want to solve different kinds of numerical, I mean non-linear harmonic oscillator or linear on, even if you want anything. So oscillatory system, it's a second order differential equation system. So you have to know how to solve a second order differential equation. So we will learn that today. So today's topic is solving ordinary differential equation. So you're not we will not focus on partial differential equations. We will basically strict ourselves to ordinary differential equation for the for this course. So basically solving ordinary differential equation, that means you can have a first order differential equation, you can have second order differential equation, and you can have higher order also. So for example, you can have nth order differential equation. So if you can understand well the first order, and then you can solve any order of differential equation. So basically, if you a second order differential equation, you can decompose it into first order equation. So how it is being done? So let me just tell you briefly now, and I will discuss it in more detail. So for example, you have this first order differential equation. Okay, so this is a equation. This is easily solvable, and so there can be second order equations also. So dx dt equal to 5t. So how you can write it? So dx dt equal to, you can write another variable, and so what is this dx dt v? So here you can write dv dt, and dv dt is 5t. So this second order differential equation, it is now decomposed into two first order differential equations. So once you know how to solve a first order differential equation, so any nth order differential equation, that you can decompose into n first order equations. So let me write it: any nth order differential equation can be decomposed and write with n first order coupled differential equation. So we will go into this more detail later, but let me just tell, motivate you why you should learn the first order equation correctly. Because any nth order, so you can in this way you can decompose it into this n first order. So there is a second order differential equation, so you can decompose it into two first order differential equation, and so these are coupled. So uh, so if you know how to solve a first order differential equation, so that means you are done with the topic of solving this differential equation. So then you can effortlessly simulate any harmonic oscillator equation. So see, they are mostly they are second order differential equation. There can be nonlinear term and so on. So so now let me go into the topic of solving first order differential equation. Okay, so this is the topic now which we will explore. So generally any first order equation, so you can write this as in the following way. So dy dt, you can write this as function of, this can be a function of both y and t. So this function, it can be very simple and it can be very complicated also. So now why, why, we know what are the rules how to solve the differential equation. So then why, we know how to do the integration. So why we bother? So for example, if you have very simple function, for example sin t, so then in that case we know that dy dt is sin t. So you can just write in this way, the sin t dt, and you know what is the integration of so it will give you y, and it will give you, so maybe cosine of t minus maybe, so you can check that, and there is a constant. So from initial condition you will get the constant and you will solve it. So okay, so this is fine and you are done with if you have very simple equation, even in that case you don't need the computer also. So you can just by hand, by the rules you can calculate what is the uh, integration of the given function, then you can proceed through. But you there can be scenarios where you can have very complex function. So for example, you can have function like this, so dy dt, so maybe y sin t, and there in this side there can be non-linear term, so y cube, and suppose exponential of minus t. So now, how, analytically it is very hard to calculate this. I mean, this is a function of both y and t, and here you have y cubed, and so you can so this is a non-linear term, because sine, it can be expanded as t minus t cube by 3 factorial plus t to the power 5 by, and so on. So this is the expansion of t. So this is, uh, so this is a cube product which is multiplied with y. So that is, this is a non-linear term, and here also we have this non-linear term. So this is non-linear, and this is non-linear also. So if you have this kind of very complicated term in your differential equation, then it becomes very hard to solve analytically this differential equation. So that is why, in that case it is handy to use this numerical integration. Sorry, so numerical integration. So there are various types of numerical integration method available. So for example, so first we will learn about the simple one, which is Euler method. So this is a first order differential. This is a first order method, and we will learn about the explicit Euler method, and then we will go to higher order method. So for example, there exists RK2 method, and there also exists RK4 method. So for today, we will focus on Euler and RK2, and if you can learn the RK2 properly, then from that you can by yourself can write the code for RK2. So you can try after today's class, or we can discuss it in the next day. So for now, let us focus on the Euler and RK2 method. So so our goal today is to take a differential equation and walk with it by step calculation. So we will solve it using the numerical time stepping. So what is the idea of Euler method? So basically, so here you have the, so let me write down Euler method. So now we will go through the Euler method. So, so what is our differential equation? So our differential equation is like this. So dy dt function of dy. So now, so for example, you will have t equal to t0, which is your initial condition, and at that point you will have a value y equal to maybe y at t equal to t0, you will have a specific value for y. So this is your initial condition, and this is your initial point which will be given to you. So for example, that is, I mean, at t equal to 0, so y is 1. So let me consider this as the initial condition. Okay, so I will, uh, when I will give example, I will state that. But for now, I mean, so consider this general point. So this is my initial point, and I mean, so you want to solve this. I mean, you want to solve it for a larger time. So for example, final time is t equal to t, and in this time range, you want to know how your y will look like. So I mean, you will have an array of t. So these are the points in t. So you want to know what is the, I mean, according to the rule. So this is the update rule for y. So according to the rule, if this is our initial time and this is our initial uh, y value, then if I follow this rule, then what will be values of y for all the t value that are present in the t array. So this is our goal. So we can, so Euler proposed a method to numerically compute this. So, and so what is the method? So basically, I mean, using, so I mean, you can, so dy dt we can write. So for example, if this is t and this is t plus delta t, so delta t is what? Delta t is the step size. So delta t is our step size, or you can call it time stepping. So for this step size, so now we can write this equal dy as t plus delta t minus y at t. So at t, I mean, you will have a certain value of y, and this t you will have another value of y. So this is your yt and yt plus delta t. So dy, so if I look at this step, so dy is, I mean, difference between these 2 points. So which is this yt plus t minus yt, and it will be divided by this delta t. So dt is our time step, and here what you will write. So in case of this Euler method, if you are following the Euler method, so this is explicit Euler method. So this will be your f at t and y at t. So there is this explicit method, and there also exists another method of Euler called implicit. So in that implicit method, so this is considered as, in that case we will consider the point t plus delta t and y at t plus delta t. But I mean, so I mean, this explicit, we will now focus on explicit method. So that is why we have written down here this yt. So this is, so this line we are using the Euler's proposite method. So this is, I mean, following Euler's method, and this is the explicit method. So if I have this update rule, then we can write that y at t plus delta t equal to y of t, I mean, almost nearly equal to, plus delta t, which will be multiplied with f t and yt. So this is the update rule by which you will update it. So I mean, you will start from t equal to 0, and for t equal to 0, you know what is your y value, and that is given, which is y0. So you'll put it here. You know delta t, and you know what is the functional form. So this functional value you can calculate at initial point. So it will give you a number. So I mean, you will get this number, and then you will add with the initial value. So you will get the first element, I mean second element, and after this task you have to perform iteratively. So when you want to perform the iterative task, you have to, I mean, use the for loop. So I mean, when you want to, so if you want to solve the differential equation, so you have to run a loop, so which will run for the length of the t array. So I mean your initial point is t0 y0, then you run the this then you update the values in y according to this rule, and so once you are updated, you will get the y value. So you can write down here. So this is the up. Okay, so let me try to solve this using let me try to solve using a example in MATLAB. Fine. So this so if you follow this rule, so you will get the corresponding y value. So now let me go to MATLAB and let me work with. Let me just write down here a simple equation which we will try to solve. It's good to start with the simple one first. So we will try to solve this equation dy dt equal to which is, so let us simple like minus 2y, and this is our initial condition. So this is the equation which we will try to solve in MATLAB. So let me go there. So let me first save it. Lecture 5, first ODE, and this is Euler. Okay, so first what you have to do, so you have to define the time array. So first let me define dt. So what is dt? So before all, let me put it here. So the good practice to write it on start of every code. So then I will specify the time step here. So 0.1, this is our time step. So let me take it for now, and then we will have the time array, so which is starting point is 0, and then we have this time step, and we will go up to, for example, let's say 10. So these are time array. Then I want to have an y array which should be of the length of the time array. So I can write it in this way: zeros, 1. Zeros you can write, here size of t. This is another command by which you can create this arrow or this array of the same length. So let me run it. You can do run in advance, or you can just simply run it. So you can see that we have created both the t array and y array. So this is your y array where you have all the elements to be 0. And this is your t array which is running from 0 to 10 in steps of 1. Fine. So all good. Now you want to implement let me just Euler integration. So here we will write down the Euler method how we are doing it. So for Euler integration, what we will do? So we will run a loop for I, which will start from 1, and it will go up to the. So let me just write it down, and then we will check will it go up to t or -1. So how we will update it? So basically initial is 0, and that is the initial condition also. So if the initial condition was different, then you can update it here. So y1, so the first element. So let me give you example with different initial conditions. So that will generalize the thing, and that will make you able to understand it more. So instead of this 0, let me okay. So the initial condition is 1. It's fine. So the first element I want it to be 1, but not 0. So this is how you will change the initial condition. So here what you are doing? So you are changing the initial. So it is your initial condition. So in this way, when you are writing a complex and large code, you can I mean uh, write something for yourself, so that after a large time when you are seeing the code again, can understand which line is. You can understand the highlight or the key points in the code. So so this is the initial condition. So whenever you are seeing the code after a very large time, so maybe by then you have forgotten what the Euler rule was. So you will understand by looking that these are my initial condition, and this is where the Euler integration is happening. So in this way, it's a good practice to add comments in your code, so that so that it is generally readable to anyone, and and they will be able to grasp the core concept, the core or the fundamental of it. So now how we will update it? So basically yi plus 1 equal to, so what is the update rule? So I have to work, so I have to put the yi. So for I equal to 1, it will take the initial value here, and depending on the initial value, it will update the y. So if we so here we have a simple function, so that is why we can write it. So for plus dt, which will be multiplied with, so 2t was our minus 2t was our function. So let me check it again. Okay, so minus 2y. So minus 2 dot star, and what is y? So you have to, in the function. So in the function you have to use the this value. So so if you are calculating if you are at t and you are calculating for t equal to t plus delta t, then here you have to put t. So that is why if you are according to the I value, if you are updating the I plus 1 value, So here you have to write I. So this is the Euler explicit method. So I mean, since you have a very simple function, so you are writing it here, or you can create a, I mean, you can create a function and you can maybe write down. So I mean, so in the you can write it in the functional form also. So first, let me show you with the simple example. Then I will generalize it to functional form. So this is your yt plus delta t. So here the update will happen, and then you will end it. So I mean this should go up to t minus 1 because in the last, so I mean, so when it is length equal to t, so this will be index will be out of bounds, so it will give you error. So this is your corresponding y value updated. So if you have your, so now let us look at our y array. Okay, so you can see that this is the y value has been updated. So these are the y values. So you can plot it. So for plotting, what you have to do, so I mean basically you have solved the ODE. So you have your first order differential equation. You are using Euler method, and by Euler method, for each of the time step, you are, I mean, you are getting what is the y values. So I mean maybe analytically you have not solved it, but numerically, I mean you know for, I mean, for intermediate time values, and if you, so you are given with the update rule that dy dt should be minus 2y. You are given with the initial condition that y at t equal to 0 should be 1, and based on the initial value and the update rule, you can now from this code you can tell what how should y will change according to time evolution. So if you want to visualize that, so you have to plot it. So for plotting, let me call it a figure 1. This will be a figure 1. So what you want to plot, in your x-axis you will have t, in your y-axis you will have y. So this is your, I mean, independent variable, and this is your dependent variable. And after that, so I mean you can change the, I mean, so you can you can make it look more aesthetic. You can put here, and I mean you can also display some name also. So display name, what you want to display, so this is Euler method. So and also what you can do, so I mean, and let me solve it. So since this is a simple function, maybe you can try to solve it by hand. So what is this function? So it is dy dt minus 2y. So what will dy dt equal to minus 2y minus dt. So if you do the integration, so let me take 2 here. So this will be ln y equal to minus t plus c. So it will be 2 here. So y will be e to the power minus 2t. So I mean some different constant. So this is your how your solution will look like. And so you are given with an initial condition y at t equal to 0, that should be 0, that should be 1. So basically means c prime should be 1. So because e to the power 0 is 1, so this will give you 1, and y is 1. So from that c prime you are getting is 1. So ultimately your solution will be this. So your solution will be y equal to e to the power minus 2t. So we can plot this in the same graph and try to look at how Euler approximation is giving us the result. So can for another graph plotting, we can call the hold on command. Then you can again plot t, and with t we want to plot e to the power minus 2t. So we can just simply write down here e to the power minus 2t. So this is your function. You want to plot this, so you can uh, change the display style. You can add some name here, display name. So what you want to display? So this is the exact solution, and you can give put x label and y label also. So let me go to legend. Then you can plot x label t. Then you can call y label, which is our y. And let me give a title. Okay, so title, this should be small, I guess. Okay, so what can be the title? So Euler explicit versus exact solution. Okay, so let me try to run it. Okay, so almost matching, because step size, it's small. So we can increase the step size and look how they deviates. Yeah, so now you can see that this is how the exact solution would look like, but this is how the Euler method is giving us. So if you have large step size, so in that case Euler method is failing miserably. So we will try to look at, try to look at this. So today's lecture we will also look at the order of error, so depending on the step size. So Euler method has the order of order of dt error. So we will look into that in in uh, more detail, so in today's class later. So now this is for a simple function. Now you can you can define a function where you will just write down the form and you can call the function here. So let me do that. So whenever you are having a function, so you are telling MATLAB to define a function here, then you have to specify what is the output. So just out, maybe Euler, and function Euler, and here you have to give input. So what are the inputs that you want to give to your, so this arrays you should give here as an input. So t and y. So t should be the array, then y should be, these two scalar you should give t and y, and depending on that, then you have to out, it will give you the corresponding output. So if you are having a function, you will end it, then you will write this out, which will be what. So here you will write down the functional form. So what is the functional form here? So so do you need to define anything here? So nothing else. So this is just 2y minus 2y. So write minus 2y, and you can write down the function here, function Euler. And so order is important. So then, so let's look at, so t I by I. So for Euler, you will be passing this ith values. So and t. So you let me try to run it. Okay, something out Euler. Okay, so these two should match because these are outputs. So out Euler, I have to write down here out Euler, and I think it should work now. So yeah, so I mean it is working in the same way. So you have generalized it. I mean you have to just change the functional form here. So if you want to solve a different equation, so let me first make the dt much smaller, and let me look at the output. So it is almost exactly. So I mean it is deviating still. So you can you can decrease dt more, and I mean you can look how they are deviating. So this will be much smaller now, I guess. Yeah. So it is almost matching. So fine, I guess. You can change the function here. So you can introduce here t, and let me try to run it. Okay, so your exact solution. I mean now the functional form is also different. So this will be not the solution anymore. So what will be the solution? Let me try to guess. So I mean you will have t here. So you will have t, and that will give you basically t square. So t square, okay, so instead of this 2t, you will have t square. So let me, okay, let me run it now. Okay, so fine. So this is where, I mean, in this way you can, in this way you can create a very complex function. For example, sine, also you can include sine t. Then with that sine, you can also have some exponential t square multiplied and so on. So I mean any kind of complex function you want to create, that you can create here. So yeah, so I mean whatever the function it is, I mean you will get quantity, you will roughly get the idea how your solution will vary with changing time. So I mean we can, instead of diverging, we can make it, I mean instead of decaying, we can make it increasing. Okay, so sinusoidal is already okay. So this is, I mean, you can play with different kinds of function to look at the output, and this is where you can generalize writing this code. So this is your Euler method. Now, let me show you what is this now RK2 method. So in case of RK2 method, so in Euler method, what you are doing? So in here, you are putting this, you are computing this function at the ith point, ith point. I mean, so at, so if you are starting from t and you want to know what is this value at t equal to t plus delta t, then you are just using the functional value at the value at t equal to t. So this is Euler method. But for RK2 method, what you will do, for RK2 method, you will look at the values at intermediate point also. So for example, if this is your yn tn, so value at nth time step, and you want to know what is the value at yn plus, so I mean, so this will be at n plus 1. So n plus 1, let this be our step number, and here you will write tn plus 1. So tn plus 1 is basically your tn plus h, or tn plus delta t. So this is your tn plus 1. So in Euler method, you are executing this functional value at this point. But in RK2, what you will do? So first, you will also use another midpoint. So in midpoint you will execute it. So first, let me define two variables. So k1, which is yntn, and then you will have another variable k2. So where you will evaluate this functional value at midpoint. So you will write here y, I mean so yn plus delta t, which is your dt or h, whatever it is, delta t by 2 k1, and here you will have tn plus delta t or h or whatever dt, you can write plus 2. So this is your k2, and based on this so here, you are using, you are evaluating this at yntn, then you are using that k1 value to compute another variable k2, and from using the k2, now you will update y value, which is yn plus 1. So value at n plus 1 time step, this will be yn plus delta t into k2. So now in RK2 method, this is your update rule. So this is update rule RK2 method. So this is how you will update the function. So here the main difference was, you in RK in Euler method you are using here k1. If you look at it carefully, so k1 is basically your f at y and tn. So your k1 was used for for Euler method, but in RK2 method, so using the k1, you are evaluating another variable at the midpoint. So tn plus delta t by 2 is basically just the mid time point, and at that point you are uh, uh, updating the y value. So this is, which is yn plus delta t by 2 into k1. So so here also, you are updating it, because you are basically taking yn plus, so delta t by 2, if that is your, I mean time step. So you have this three. So this is yn tn, this is yn plus 1 tn plus 1, and this is your, delta t by 2. So how you will get the point here? So you will, if you use the Euler method, so you will get values at y. So let me call it yn plus half. So which will be yn plus delta t, and now, and what is the difference? So it is delta t by 2, and you will evaluating at t and yn. So which is just basically your k1. So you will get yn plus delta t by 2 k1. So this is your yn plus half. So you are just using that value here. So you are evaluating at half point. So so this is your, you are putting here yn plus half. Yeah, this is your tn plus half, and from that you are calculating the k2, and you are now, once you are done with the k1 and k2, you are so when you have gotten this k2 value, so what is the y value here? So using that value, you are updating it. So here you can see this yn plus, so plus delta t, and instead of writing here yn, so you are using value of this point. So that is the main change between Euler method and RK2 method. So let me show you how to do this in MATLAB. So let me first set the script. So lecture 5 fast ODE, and this is RK2. Fine. So let me copy it because almost most of the things are same. So this is your functional form, and I mean we'll change it. So let me call it RK2. Press Shift Enter to rename one other instance in this here. So I mean here you have to change everywhere where it is written Euler. So I rename it RK2. So it is RK2 now, and I have to give it the values. Okay, so I mean I have to be careful here. So first, so how can you write this? So you have to define what is your K1 and K2. So what is your K1? So K1 is basically uh, this function evaluated at Ti Yi. So this is your K1, and what will be your K2? So K2 will be your this function evaluated at Yi plus delta t by 2 K1. So I have to write it here. So this is at Ti plus, so what is my time step? So this is dt. So Ti plus dt by 2. So this is my time now, and here I have to write Yi plus K1 into dt by 2. So y1 plus k1 yi plus k1 into dt by 2, and this is ti plus dt by 2. So this is I mean k2, and how I will calculate this yi plus 1. So this is basically yi plus delta t into k2. So I mean delta t into, instead of this I will just simply write here k2. So now that should give me the result. So let me remove this one now, so that I can check with what is already written here. So let me run it. Okay, so this is working. So this is not Euler. So just change where it is written Euler. So this is RK2. This is RK2. And here, is there any other instance where I should change? Yeah. So RK2. So I mean you can use the fourth order Anjagutta function. So you can Google and search it. So RK4 method formula you can search for. These are different kinds of RK4 method. So let me, I mean, include this in the code. So yeah, so this is, I mean, first order. So this is up to RK2. I mean second order. Then you will have K3, which is this is, I mean this Tn. So you are evaluating at midpoint here also, but this instead of k, so first you are using k1 to get k2, then you are using k2 to get another variable k3, and from k3 you are getting, I mean you are getting the k4. So let me try to implement this in the code. So let me save it as different. So RK4. Save. And here what should be the k3? So k3, instead of k1 you will write here k2, and what will be your so k4, it is basically t. So there should be another variable k4, is k3, and there will be k4, which will be a function at tn plus h. So tn plus h means this should go away, and we have yn plus h into k3. So this is your yn plus this is your a. Here you should have h, and here you should have k3. So you are done with k4. So using that k4, you can. So what is the final form now? Yeah. So this is the final form. So yn plus 1 equal to yn. So let me update it. So tn plus 1 is tn plus 1 is, so that is fine. And this is, I mean, h by 6. So by 6, and here you will have k1 plus, so let me see it once, k1 plus 2k2 plus 2k3 plus k4. So k1 plus 2 to k2 plus 2 to k3, and then we'll have k4. And let me run it. Okay, so you can see that it is working. So I mean, this is, I mean, the higher order you go, I mean, it is computationally more expensive, but it is more accurate. So let me show you with TT1. So this is the output of RK4. This is what the, I mean, let me try with a different function, e to the power minus 2t, which was initially we were checking, and let me run it. Okay, so yeah, you can see. So this is the exact solution. So let me plot it up to 4. In that case, it will be more good way to visualize. Zero point 0.4. At least, I mean, we will have 10 data set. So yeah. Okay. So for up to 4 and with dt 0.4, so even if you have this 11 data point, you can see that the so this is not Euler method. So this is RK4. Okay, so RK4 method, even for 10 data points, 10 11 data points, it is almost matching. So let me check with RK2 what is the case. So let me remove this, and this is RK2, and this is RK2, and let me go up to 4, and the step size, let me make it 0.4, and let me check what is that. Okay, so little bit different, not exactly matching with RK. And Euler, we have obviously we have observed earlier, it was, I mean, very, I mean, different compared to the exact solution. Let me show you once again. Okay, so this is the solution of Euler method. So this is Euler method. This one is exact, and this you are getting from Euler. And this is it's huh, start from the, this is Euler. You can see this is the exact result. This is we are getting from Euler deviating. Then we are doing with RK2 much closer, but not good enough. And this is with RK4. So RK4. Let me put it here. Figure 3. Let me run it. Fine. You can see in Euler there is a deviation, with RK2 a little bit less deviation, but still there it is, and with RK4 it's almost exactly matching. So you have 11 data points. So even with very small number of data points, RK4 almost give you good accuracy. So that is why it is it is computationally expensive, because you have to you have to evaluate this functions k1 k2 k2 k3 k4, then you are using this. So it will be more computational heavy and time heavy, but it will give you good enough result for your case. So now let us look at the order of error. So in case of Euler and RK2 method, so how we can know the order of error? So let me show you that. So in Euler method, what you are calculating? So you are calculating yn plus 1 equal. So order of error. So in Euler method, we have calculated yn plus 1 as yn plus h function evaluated at t and yn. So but this is, we know that this is not the true solution. So how the true solution will look like? So if you do the Taylor series expansion, then yt plus h, generally we how we write it. So from Taylor series expansion we write is that yt plus h f of t y, f at ty, then we have this h square by 2 factorial, and here we have f first derivative, then ty, and then we will have this, we want to find the lowest order of error. So after that you will have this h cube term, so h cube, and there will be second derivative of f and 3 factorial and so on. But then so since we have so this is the Euler solution, this is the Euler solution, and this is the exact solution which you are getting from Taylor series expansion. So what is the order of error? So in each step, so the order of error that is called as local error. So local error is order of error, or we can call it error in each time step. So when you are evaluating yn plus 1 from yn, so for that one time step we will get some order of error, and so that error is known as local error. So local error, as you can see, so we can call it local error or LE, so which is true. So let me call it true. So y true value at t plus h minus yn plus 1, and so this is the of same order, this is of same order. So there is no h square term. So it will be of order of, so it will start with order of h square, then you will have term with order of h cube and so on. But the highest order of h, I mean lowest order of h, so that is h square. So this is the order of local error. So in case of Euler method, our local error is order of h square, and what will be global error? So global error will be error in total time. So our total time, so how many steps are there? So if there are total n step, then we can write n as t by h. So because this is our time step and this is our total time. So for global error, we have to multiply the local error with total number of steps. So if I do it, then we will find out that global error is order of h. So if you have larger, so for example, in our given case, so if you, and so now this is for RK2, Euler method. Similarly, if we do the calculation in same way for RK2, so for RK2 method, what you will see? So we will, so let me do it for RK2. So we have K1, which is function evaluated at Tn, Yn. Then we have K2, which is function evaluated at Yn plus h by 2 K1, then Tn plus h by 2. Then we have then Yn plus 1, we can write as Yn plus hk2. So if you look at it carefully, so this k2 term, it has, so I mean, so this k1, so if you look at it carefully, so there you will have a term up to order of h square. So k2, in place of k2 you will replace this, but here you have k1, so which has which is this function. So this h and this h will be multiplied, so it will give you h square order. So yn plus 1 has the highest order h square. So now if I again want to look at the difference between the true value at yt plus h minus yn plus 1 from RK2 method, then we will see that this will be equal to order of h cube, it will be the lowest order term, then you will have order of h to the power 4 and so on. So but here, so the thing is that the local error, so I mean, or the error in each time step, so it is order of h cube in place of RK2. And if you want to calculate the global error, so which is basically local error multiplied with total number of time step, and this total number of time step is total time divided by h, so it will be of the order of h square. So in case of RK2, we can see that order of h square is the global error and local error is of the order of h cube. So I mean, so in our example, so if we make so for example 0 to 10, so if I make this dt to be small, so so if this dt is 0.1, then you can see that so for 0.1 what will be h square? So it will be 1 by 100, and what will be h? So it will be 1 by 10. So this is for Euler and this is for RK2. So for RK2 method, we can see that the order is is lower compared to the Euler method. So that is why, I mean, in this way you can show why Euler method is more suitable. RK2 method is more suitable. So due to low error, RK2 is more suitable compared to Euler method. And in this way you can, I mean, calculate the order of error in I mean in case of RK4 also. So so in this way, so this is how you can solve any first order differential equation. So you can in the code, what you have to do, you have to change the function only. So your function can be very complex, and what you have to do, you have to just change the functional form here. So if you change the functional form here, so in this code here, it will calculate what will be your uh, uh, what will be your the uh, the result of your integration of the differential equation given. So you can take different kinds of differential equation and can try to play with it. So this is all for the first order differential equation. So after that, we will proceed with how to solve a second order differential equation using this. I will show using Euler method and RP2 method. So so let us take just a quick 5 minutes break, and after that I will show you how to do that. Okay, so now we will proceed with how to solve a second order differential equation. So as I was telling earlier that any second order differential equation, so solving second order ODE. So we will solve the second order differential equation using Euler and RK2 method, and I will leave the RK4 method for you guys. So let me start with the equation which we will let me start with the equation which we will often use, so which is the x double dot plus omega square x. So this is the famous harmonic oscillator equation, you know. So we'll write here 0. So and so what you can do, so you can define so let us call x as x1. So what is this x prime? So x or the derivative of x, we can call it x1 derivative, and let me rename this as x2. So what is basically x1 x2? So, it is basically the position and velocity if you think of a harmonic oscillator, because if you take time derivative of position, so that will give you a velocity, but for generic use I am just rewriting as x1 and x2. So x1 is your one parameter for which the differential equation is written. So it is a second order differential equation for x. So the first order derivative, you are considering this as another variable which is x2. So now how the equation will look like that you have written. So from this one you can write that x1 prime, x1 dot is x2, and x2 dot is basically minus omega square x1. So this is your differential equation. This is your first order differential equation which you are getting from the second order differential equation. So how can you write this in matrix form? So dx dt x1 x2, and here you can write x1 x2. So this should be x1 prime is x2, so it should be 0, it should be 1, and x2 prime is minus omega square x1 and 0 x2, so it should be 0. So this is your so now you can call this x1 x2 matrix as capital X. So x1 x2 this. So in MATLAB you will use this matrix. This is your x, and this matrix, let me call it as f. So right hand side is basically f x t. So you have this kind of equation and you want to solve this. So how you can use the Euler method for this? So let me show you in MATLAB, because you are basically done with the problem. So you have this dx dt. So you have the similar equation. So you have this dx dt f xt. But here now, so in the previous case for for first order differential equation, it was a scalar number, it is scalar. So it was 1 cross 1 matrix, but right now this is 2 cross 1 matrix. So depending on the order of differential equation, so if you have nth order differential equation, so this x will be your n plus 1 matrix, and here you will have a form which will depend on the x matrix and also on the time. So you can have so this is so you effectively you will have to use the same logic, but instead of passing only the scalar, now you have to deal with array and matrices. So let me show you how you can do that. So let me save this as lecture 5, second order ODE Euler. Okay, so let me proceed. So I mean we will again define the time step here. So maybe 0.1. Uh, then we will have this T array, which is start from 0. Step size will be dt, and you will go up to. Okay, so let me just write it small t. So you will go, for example, up to 10 maybe, and then you have to put some initial condition. So for example, your position. So if this is a second order differential equation, then you have to mention two initial condition. So you have to, I mean, for example, in case of harmonic oscillator, you have to mention what is the initial position and what is the initial velocity. So and before that, so let me go again here. So in Euler, what we are doing, so here we are defining this y array, which is zeros size of t. But now, since I mean you are dealing with a second order differential equation, so here instead of this I mean zero, so you have to also specify the row. So I mean here you will have two rows. So first row will be for x1 and the second row will be for x2. So this is your, I mean, so let me write down here. So this is, I mean, x1 x2. So first row along all the column you will have the x1 values. The second row along all the column you will have the x2 values, and then you have to specify an initial condition. So okay, so let me call it I mean x, and so what will be the initial condition? So x, I mean along all. So suppose, and for first column, so let me run up to this so that you can understand. Okay, so let me tell you what is happening here. So this is your x array. So this is your time array, which is 101 points, and along the first row and all the columns here you will store what will be the x1 value, and along the second row and along all the columns, so here you will store what will be the x2 values. So now you have to specify some initial condition. So if I don't specify the initial condition, then I mean initially we have created all, I mean all the elements are 0. Fine. So now you want to store the initial conditions here. So that is why what we have written. So I mean all row. So first one is row. So you will overwrite the values of all row and the first column. So this is your first column and all row. So here what you will put. So 1. So notice here I have put the semicolon. So because I want the values to be stored here and here. So if I don't put the, so let me just put 1 here, and let us look at the output. So you can see that is 1 1 now. Now if I don't put the semicolon and just put comma, then we will see that this will be 0 and this will be 1. Okay, so so for this it was not happening. It is not happening. So you have put down all the. So here you have mentioned that you will store along the first column only. So you are storing here 1 and you are storing here 1. So for I mean for practice you can put here semicolon. So in this way you will store the values along the column, so that you keep in mind that you are storing along the column. So I mean you can mention some comment here. So if you want, so maybe I mean something like x0. this is our initial condition, which is 1, and what will be the other condition? So if you think of it as a harmonic oscillator, so V of 0, that is 0. Put here 0. So if I make it here 3, so I mean then the third column will be updated. So for convenience, I will show you that here you can see that it is 1 0. So I mean, so that is why it is written 1 here, and it is the row value. So for all the rows and along the first column, you will update this value. So I will run it, and it will 1 will be stored here and 0 will be stored here. Okay, so I have created the time array. I have also created the array for position and array for velocity, and also I have stored the initial condition. Now what is the next task? So in Euler, so let me go to the Euler one. So I have stored the initial condition. Now here I have to so let me just copy paste everything so that I don't have to again come here. Okay, so function Euler, so 2D, because I am doing a second order differential equation maybe, and here what you have to give, so instead of y you have to, let's just write here x, and what should be the, okay, so let me look at the function later. Let me fix it here. So how will this look like? So basically uh, here you will have, so let me write down this is dx. So dx, and you want to call the function, so you are calling the function here, and then you have to pass this x value. So because I mean so then how you will write it? So here you have yi, so you will so that is why you will write here, so along, so you will pass values of all the rows. So you want to pass the position and velocity both, and you want to do it for ith column. So that is why you have to write here this, and also you want to store, for this problem it is irrelevant, but you want to also uh, pass the t value, and also for this problem, so you have the omega here. So let me define omega. So I have to define omega somewhere, which will be the frequency. So let it be 1. Fine. So you are passing the omega here. So how will your this now look like? You have to maintain the order t, x, t, and omega. So you will pass it. So how it will calculate this? So that let me update here. It is x, and I will update along all the rows. So here we will have x, all the rows, and the ith column, plus dt into this function. So here you can just simply write dx now. So dx we are evaluating from the function, and that we are putting here. So we are getting this x I plus 1. What is the value for I plus 1? So now here you have to write down the functional form. So what is the functional form here? So once you are so what you are passing here? So you are passing here a column vector. So if you look at it carefully, so you are selecting values along all the rows and for ith column. So you are effectively passing a column vector, and so the first uh, value of the column vector, which is x1, that will be your position, maybe small x, and v, that will be your x2. So the first value of the column vector which will be your position, and the second value of column vector will be your velocity. Then what should be your, I mean, so if you look at this again, so what is your dx dt? So dx dt is basically, you have x2, so x2 is v. So let me write it here. So dx is v, and what is dv? So dv, or this, so x2 prime, so this is minus omega square x1. So let me write it down, which is minus omega square, and you will multiply with what? So you will multiply here with x. So let me write down here x. So you will get this dx and dv. So once you get this dx and dv, so you want to store it in this. So here you have this. In this, I mean, you want to store in an array and you want to return it. So you can just in out Euler you can store this too, and you want to store along column. So you will put a semicolon. So dx dv. Uh, okay, so maybe it will work now. So you want to suppose plot first row and all the column values, and you also maybe want to plot second row and all the column values. So this is your position, and this is your velocity, solving harmonic oscillator ODEs using Euler. Let me run it and let us see if it is working. Okay, fine. So x1 and 2. So that is why it is exactly matching. It should be x2. Yeah. So you can see that position, I mean, these are initial condition. Position is 1 and velocity is 0. So it is starting from 1, and you can see it is exactly, I mean, following a harmonic oscillator, but I mean, it is not exactly following, because you have this, I mean, here you can see that it is not matching. So I mean, in harmonic oscillator, this maxima or minima points, so they should be same in each cycle, and that is maybe due to the step size. So you can try to decrease the step size even more. Yeah, and you can see that now it has been improved. So I mean, you have to be careful about what the step size you are using. So I mean, this is the way. So what we have done, so basically we are doing exactly the same thing what we are doing earlier. So we have this equation d2x dt square equal to minus omega square x. So we have written down dx dt equal to v, and dv dt equal to minus omega square x. So I mean, this x and v, so you can write as d dt of x v as matrix, and here we have v minus omega square x as matrix. So this is our given equation, and we are given with the initial condition, and we are defining a function where I mean, we will give this as input, so it will evaluate this, it will evaluate this, it will store it in a column vector, and it will give the output. So I mean, and we are basically solving the Euler method, which are doing for the for the 1D one first order differential equation case. So this is, in this way you can write the differential equation for first order for second order ODE. So I mean, you can so you can change the function if you want. So I mean, this is a simple function. Now you can have a complicated function also. So dx dt equal to, suppose, I mean, consider the case of damped harmonic oscillator. So it will be what? So I mean, damped oscillator equation is, so here you have this gamma x dot. So we will So what will be the case? So here you have you will have minus gamma v. So let me so now if we want to solve it, so what will be the solution? So dx dt equal to, you will have v, so it is always v, and dv dt is minus omega square x minus gamma v. So you have in the matrix you have to include the extra term. So whenever you are writing the function, so let me do that. Okay, so maybe it is not working. So let me wait for 1 minute. Yeah. So now you have to also specify the function what gamma is. So 2D, let me call it damped. So you have to make changes here also. Yeah, 2D damped. And what are the things that you need to change? So you have to define what is gamma. So gamma right now let's say 0.1, and what are the other things I need to change? Yeah. So here dx dt is phi and dv dt is minus omega square x minus gamma v. So you have to write down here minus gamma, and you have to multiply it with v. So if I run it, so what is this? So let me write down the name, second ODE Euler, and down here damped. Okay, some error. Okay, so here you have four input argument for the function, but if you look at here, so you have to specify the fourth one also. So gamma, let me run it. Yeah, you can see that it is decreasing. So let me increase the time more so that you can see the decreasing behavior. Let you able to see 50 dt. Let it remain same, and let me close this anything. So this should, I will suppress the output here. Is there anything left for suppressing output? Okay, so now it is working. So let me run it. Okay, so nice. So you can see that this is how its position is slowly decaying, and also how the velocity is slowly decaying. So you can also change the function. You can input non-linearity also. So maybe you can introduce here x cube if you want. So this is x cube, and let me run it. Okay, so it will change the solution. So you have to you have to know what the physical system is and how it is behaving, but the idea is same. This is a process of solving differential equation. So you can have first order differential equation, you can have second order differential equation, you can have even third order differential equation. So for third order, so here you have to, what are the changes that you have to do? So you have to define here three row, and you have to define another specify another initial condition here, and what are the other things that you need to change? So so here uh, so you have dx dv, and you will have another so maybe p, which is x, x3 value will store in p, and you will have equation for p also. So and this dx dv dp, that will put in the output value, which will go here. So this is the idea is the same. So once you are comfortable with solving first order and solving second order, then you can extend it to any order of differential equation. So you can, I mean in principle, you can work with any order of differential equation with any kind of complex analytic function. So this is the Euler method. So now in the same way you can do this in for case of RK2 method also. So let me show you how to do that. So out function Euler, and let me call it RK2. Here you also have to change RK2. So how you will proceed here? So for so here you need to define this K1 and K2, which you are doing earlier. So K1 is basically your this function evaluated at this point. Then you will have K2, which will be your this function evaluated at Ti plus 0.5 dot star dt. So this is your t value updated, and here what you will write? So you will write x plus. So here you will add plus 0.5 dot star dt dot star. So you have to put a dot star because you are having here this k1 is now I mean vector. So here you have to write this k1. So now it should work, and this dx is not needed right now. So and here you will just write down k2. So it should work. So what will be the name? So Euler second ODE, and this is not Euler, so this is RK2. So let me remove this. Okay, so there is some error, line 37. So let's square x minus gamma b. So look at it carefully. Hmm. This matching. So this functional form will be same. So let me just copy it because it is showing error in this function. Let me run it. Fine. Okay, so this is how you will get the solution for RK2. So I mean now here for RK4 what you will do, you will calculate the K3, you will calculate K4, and from that you will get so what is your X I plus 1. So let me do that. So for K3 what you will do, Control C, let me copy it. So here you will have K3 and here you will have K2, and after that you will have K4, which is basically here you will replace this with K3 and this will be 1, this will be 1, and here what you have to do, so you will this will be replaced. So first let me go to that line. Yeah, it will be the update tool dt by 6 k1 2 k2 k3 k4 whatever it is. Second will be rk2 dam. Okay, and let me run it. So now it is rk4, so let me rename it. Shift enter. Everyone will be changed here. Now save. It is saved as rk2 but it is rk4. So let me run it. Yeah, and I mean for rk4 if you have very, even for small data point, I mean it will almost match with your exact solution that you know. And so that is how I mean we can calculate, we can look at how the, so this is the visual representation from the, so we are given with only the differential equation with initial condition, and I mean so frequency gamma that you can take. So now you can play with, so for example you can increase the gamma and look at how the solution will behave. Because you can see that it is changing, so try to play with it more. So maybe gamma larger than omega, and we know that if you look at position, so that is I mean so we know that we have different cases, over damped, under damped, and critically damped. So I mean this is a starting point, so you know how to solve a differential equation using this Euler method and RK2 method. So you can take any differential equation, you can take a differential equation of any order, you can take the initial condition to be anything. So here frequency you can change, and I mean you can play around with parameters. And also I mean so so in the next day, so I mean we'll start from here. So this is our basic, so harmonic oscillator equation. So first I will review the concept of oscillator. What is a harmonic oscillator? How, what is a damped harmonic oscillator, over damped or critically damped? Then how the solution will look like, and we also explore how they will look in the phase space also. So I mean try to play with different kinds of differential equation and try to solve it. So I mean try to be comfortable with this, how to solve a differential equation. And also we have also looked at the order of error also. So rk2 is better, and for rk4 if you similarly you can calculate what is the order of error for rk4 also, that you can I mean look at it. So maybe it will be up to order of 5 maybe, so you can check. So that is why rk4 is the most I mean it is computationally expensive, but this is I mean most mm, uh, uh, it gives you the most accurate result along this if you take all these methods, Euler, rk2, rk4. So rk4 gives you the best result, but it is computationally expensive. So yeah, so see you in the next class.